what we can write is principle of reversibility of light. According to this principle, object and image positions are called conjugate points, and if their positions are interchanged, then the light ray will retrace the path. So once you change the interchange the object and image position, what you can expect is that the light ray will retrace the path, and this phenomena is called principle of reversibility of light. This is very crucial to remember. Also, let me highlight these conjugate points. And the retrace. So these are the three keywords you should be aware of. So object and image position is called conjugate point, because if you put the object at one point, the image will be at other, and vice versa. And in conic section, okay, so now this is the point which I would like to highlight separately. In conics, the foci are conjugate point, that is, if object is at one of the foci, the image must be at other focus. So in conics, this is a property. Like if you in conics, we always have the two foci, and if you keep the object at one focus, the image will be at other, and vice versa. Okay. So this is something which you can just remember. Now we can move to the next concept called spherical mirror. And because most of the formula that we are going to derive will be for this mirror only. So spherical mirrors means the geometry is a sphere. So you cut a piece of a part of a sphere, and you call it spherical mirror by polishing one of its sides and making the other side as a reflecting side. So what you do is you simply take a mirror. Then what you do next? You take a part of it. So you can take part from anywhere. And then after taking this part, you simply polish. So if you polish the inner surface like this, then outer becomes the reflecting surface. So the surface will be the reflecting surface. And if you polish the outer surface, this becomes the reflecting surface. So if the bulging outside is reflecting, what we call?
Convex.
It's called convex mirror. And when the cave side is the cave inside, you can see this is like a cave. So the reflecting surface is like a cave. So what we call? Concave. So convex and concave are two nomenclature, which is based on which side you polish and which side is the reflecting side. And because every spherical mirror is part of some sphere, so in every sphere, what we can have is a center. So this arc having this center, so this center is called what do you call? Center of curvature. This is called center of curvature, which you know from class 10th also. And the reflecting area of a mirror, you can see this is the reflecting area of a mirror. So if you think a mirror as a, draw this as something like this. So essentially, mirror is three-dimensional. So we only draw the two-dimensional view in drawing the diagram. But this is like a mirror. It's like like a ball shape. We remove this part. So if this is the reflecting mirror, okay. So the center of the curvature is the center. Okay, now the center of the sphere of which the mirror is part of is called center of curvature. Now, what is interesting here to understand is the light reflecting area. You can see the light can enter through this circle of radius r. Let's call this radius as r. So the light reflecting area, or you can see the light that can enter in the mirror, is up to what area? So what is the area up to which the light can enter? So light reflecting area is equals to pi r square.
Yes.
So what is the diameter? We can say diameter is called 2r. Now diameter is called the longest side, the longest linear dimension of light reflecting area, and the linear dimension, the longest linear dimension of the light reflecting area is called
Aperture.
aperture. So this is called aperture. Now the light reflecting area will also have center. So in this case, this is the center. So this is the center of the light reflecting area, and what we call this point? Pole of mirror. So center of curvature is the center of that sphere from which the mirror is a part of, and pole is the center of the light reflecting area, or you can say center of aperture in a way. You can think that. In geometrical optics, generally we employ very small size mirrors to keep the paraxial approximation intact. So we'll come to that, what is paraxial and what is marginal rays and what is paraxial approximation, which is the backbone of derivation. So the pole of the mirror is clear, I hope so. So now pole of the mirror and the center of curvature are called the geometrical property of mirror. Now, of course, you do not decide by any mathematical thing. It's just geometrically decided. So the center of curvature, pole of mirror, both are geometrical property, and the distance between them, what we call the distance between the pole and the center of curvature is called
Radius of curve.
radius of curvature. And I hope these things are well known to you guys.
Yes, sir.
I'm not writing in detail, just a recap. So this is called the radius of curvature. This is the center of curvature. And because we have a point called pole and a center of curvature, so from any 2 points, how many line can pass? Exactly one.
One, yeah.
So the line which passes through these 2 points is called principal axis of the mirror. This is called the principal axis. So first we define the center of curvature, then we define the pole, and once we define these two, we define the radius of curvature. Once we define these three, we draw a line passing through the pole and focus, and we named it principal axis of mirror. So this is the definition of principal axis. Okay. So once you create a mirror by taking a small piece, a small chunk of a sphere, then these things are all geometrically defined. Now I haven't used any concept of light so far. Light is not involved in all such definition. So these are called the pure geometrical construct or pure geometrical answers. So now comes the other definition. Like what? So the other definitions are, so I'll introduce the concept of paraxial and marginal rays. So concept of paraxial and marginal rays. So for every mirror which you create, let's say if this is the mirror, mirror of the part. So let me pull this on this side. So which mirror is this?
Concave.
So if we draw the principal axis by joining a or by drawing a line passing through the pole and the center of curvature. So this is the pole of the mirror and center of curvature is somewhere here. Let's say. So paraxial rays are the rays which are very close to the principal axis, like which hits the mirror very close to the principal axis. at a very small angle. So any beam of light which will hit the mirror close to principal axis, or you can say near the pole, such light is called parallax. Okay. So for example, we always think light as a beam, not as an individual light itself. So if a light is coming like this, or not light means a beam of light, and a beam of light will have how many rays? Infinite rays. So however thin you may think of a beam, however thin, it will be a bundle of how many rays? The answer is infinite. So when this beam will hit the principal axis very close to the, when the beam will hit the mirror actually very close to the principal axis, what we call it parallax. It may have some very small angle alpha. The alpha may be tending to 0. Generally, that is the case. What you need to realize that parallaxial does not mean parallel to principal axis, because in many books, especially in the high school level, they draw the parallaxial line as parallel to the principal axis, but that is a wrong notion. The parallaxial need not to be parallel to the principal axis; it can be at some angle. And as you go away from the principal axis, and if you hit the mirror, maybe somewhere here. Again, I am taking a parallel beam of light. So the beam itself is parallel. This is the takeaway. The beam is parallel. This is called the pencil beam. You can call it, this is called pencil beam. And where they are hitting it, the answer is obvious. They are hitting quite far from this principal axis. Such beam is called marginal rays. Okay. So
So also
our,
parallel to each other.
yeah, they are parallel. The marginal rays are always the inner beam. The rays are parallel. The overall orientation may be at some angle, maybe horizontal, maybe at some slant. So when the rays come from a distant object, let's say star or any uh, far point, or you can say infinity, every beam of light coming from distant object must be assumed parallel to itself. Now, it doesn't mean that the rays will be paraxial. Distant object will give you parallel beam, but beam can be marginal also, beam can be paraxial also. So what is
Sir,
the
I didn't understand the marginal and paraxial.
marginal? Means something which hit the mirror away from the principal axis, the edge, the end part of the mirror.
And paraxial?
Paraxial close to the principal axis. You can see it
Okay.
is hitting the mirror here. So this is
Yes.
close to the principal axis, no?
Sir,
And it is here away from the principal axis. Yes, sir.
so marginal and paraxial can be part of a same beam or different beams.
We don't take a same beam. Of course, if a beam is spread, then we can say that, yeah, then we cannot distinguish between, okay, exactly where is paraxial, where is marginal. What I'm saying is that out of the entire beam, which is spread throughout, of course, of course, some beam must be in between also. It is not possible that we can't have beam like this. We can draw this entire, fill the entire gap with uh, rays only. Let me quickly fill this gap. So a small portion or segment of such beam near the edge we call marginal, and near the paraxial we call paraxial, and near the principal axis we call paraxial. Then we will not name such rays in between. Intermediate, something like intermediate beam. So generally in literature, what we do, we take care of only the extreme cases, not the individual cases. I hope this is clear.
Yes.
So of course we have all sort of beam. We have the marginal and till paraxial. It's not like we have a discrete beam. That beam will be here, then there is no beam, then again beam will appear. No. What we are considering is a small piece of it, or a small chunk of it. And the beam closer to the principal axis, maybe you can take few thousands, few millions, few trillions, but it should be very close. That you can club into a beam called paraxial. You can call this is a paraxial beam. Okay. And if you go towards the edge of the mirror, then you can club those beam as marginal rays. Okay. So paraxial rays, and this is marginal rays. The rest in between we don't care. What its name, what it should be, it really doesn't matter. Okay. Now the geometrical optics, the derivation of geometrical optics that you have seen so far in high school in class 10, those were derived for the paraxial rays, not for the marginal rays. Okay. So paraxial may be parallel to the principal axis also. Paraxial may not be parallel to the principal axis. And the beam which is parallel or slant with respect to principal axis. See, I'm saying beam. Beam is a collection of parallel rays. I'm saying a beam is inclined to principal axis, or beam is parallel to principal axis. So in such case, when we have a beam which is either parallel or at some angle to the principal axis, it gives rise to the two different concepts, and one is called the primary focus and another is called the secondary focus. So now we need to understand these two concepts in detail, and the concept is called concept of primary focus and secondary. Secondary focus is not unique, primary is unique. So it can be anything. So what exactly is this? So for that purpose, we'll redo the mirror again. So in geometrical optics, this portion is the difficult portion. Not very difficult, but slightly. So focus is something that we don't define geometrically, we define optically. So focus comes through the definition. So what exactly is focus? So far, everything we defined was purely on a geometrical construction, like it was purely geometrical construct. Now what we want to define is focus, but that is not a geometric construct. So focus depends on the beam, the light. So what do we call? What is focus? So to understand the concept of focus, we need to go to deep. We need to go to back to the laws of reflection. So focus is defined for a beam, a parallel bunch of rays. And this parallel bunch of rays may be parallel to the principal axis, may not be parallel, right? So imagine a ray coming parallel to the principal axis. So it's a beam actually, not a single ray, it's a beam of light coming like this. So a beam of light, what we denote by a single light. Okay, it's like understood. You have a beam of light, and this light is coming parallel to the principal axis. Parallel to the
Principal
so
axis.
a ray is parallel, a beam is also parallel. So within this beam, we have infinite rays which are also parallel to each other, as well as parallel to the principal axis. Now, don't think about the spherical mirror. Just think about the basic law of reflection. To write the law of reflection, we need to draw the normal at the point of incidence, correct? In a spherical object, how you draw the normal? For any spherical object, how we draw the normal?
Sir, perpendicular to
So
the
it will
tangent.
pass on curvature. Yeah, the time.
Any line which you draw from center will be perpendicular to the mirror, right? Because in a
Yes, sir.
circle, the radius and tangents are perpendicular. That's simple. And therefore, if I draw a line like this is called the normal to the mirror. This is the normal to the mirror. Do you realize this? Yes or no? Do you realize?
Yes, sir.
No, this is the most important part which you need to take care of. How to draw normal in a curved surface. For a spherical, it's pretty easy. Now, if this angle is theta, which is then this becomes the angle of incidence, isn't it? And this is also theta because alternate angles. Is this clear?
Yes, sir.
So
Yes, sir.
as per the laws of reflection, the light will reflect at what angle? With respect to normal? Same angle?
Theta. Yes.
Theta only. So a parallel beam which was coming like this will pass through like this, pass through the, or it will intersect the principal axis. Now, by definition, wherever the parallel beam after reflection intersects the principal axis, this is called primary focus. Why I'm saying primary focus? Because the parallel beam is passing through the principal axis at this point. And the beam is not just parallel, it is parallel to the principal axis. So when beam itself is parallel to principal axis, then the focus is called prime. The moment you take the tilted beam, the beam at some angle, that will lead to the concept of secondary focus. So this is called primary focus. Now, can we say that primary focus is a unique point? Can we say? No. So what is focal length? I hope you have heard this name, focal length.
Yes, sir.
So focal length by definition is distance of pole and focus. Distance between pole and focus. Correct? And that is very much obvious. P to F. But the question is how you're going to calculate the P to F distance. How? So you have to do it from geometry. So if I call this as x length, let's say CF is x, then let's call this as n. No. So the Fn will be also x from the property of triangle. Equal
Yes, sir.
angle will have equal sides. Then the focal length is actually PF, and PF is how much? R minus x. Can you see that? Because P to C is the radius itself, correct? P to C is radius, and out of radius, if you subtract x, what you get?
R minus A.
R minus x, which is the focal length. So the formula for focal length turns out to be how much? R minus x. And x, how we can calculate? It's very easy. You can drop a perpendicular from here. And the C to N is also R because it's the radius only. So can we say that 2x cos theta equals to R? Can we write in this triangle? Can we write, guys, 2x cos theta equals to R?
Yes, sir.
Yes, sir. Yeah.
So x turns out to be R upon 2 cos theta. And you can see that this is quite a different formula as you have perceived from the high school. This is the actual formula of focal length. And I'm talking about the focal length of the primary focus. Now the next question is, can we have unique primary focus? The answer is no. Why? It depends on theta. And theta depends on where the light hits the mirror. Because as you go, let's say if I draw a light ray somewhere here, now tell me, will this be a small angle or big angle?
Small angle.
So the focus will change. So you can see,
Yes.
if you draw the normal like this, the light ray will go like this. Correct? So a small angle means what? The closer you go to the principal axis, the farther will be the focus. Do you realize this? The closer you go to the principal axis, the focus will shift like here from somewhere here. And then if you draw even closer, the focal length will go even away somewhere. So how many focus we can have? The primary focus is having no like finite value, because as I change the theta, and the moment you move closest to the principal axis, the theta becomes
Small.
0, because the light ray will become parallel to the radius, which means it will just retrace the path, something like that. But as I said, we don't have single ray, we have a beam, and beam will have some rays away from the axis, although very close, but beam will have some rays away from the axis. Understood? And therefore, the ray which is slightly above the principal axis will bend downward, and therefore it will give you some point of intersection. And that point of intersection we call primary focus. So the question is, if theta tends to 0, what does it mean? Okay, I'll do it on the next page. So because the focal length we obtained is r into 1 minus 1 upon 2 cos theta. So for paraxial rays, what's the condition? If rays are paraxial, then theta will tend to 0. And what is the cos theta value then? cos theta will be 1 because cos 0 is 1. And you can see that this was the formula which you used in the class 10th. F equals to r by 2. So is this formula always valid or is only valid for the paraxial rays?
Only valid for paraxel.
Therefore, if you derive the formula of geometrical optics with this assumption, the formula itself is a dependence on the paraxial rays. It means the image formation for a given object by a mirror, what we call the mirror formula, was meant for the paraxial rays, not for a general ray. Okay. So if I draw the focus, let me draw something. And these theoretical questions are very important from the point of view of JEE. JEE will ask you some deep question, and you won't be able to answer if you don't realize under what condition a given formula is applicable. When we should not apply the formula is the important concept in geometrical optics. So more than you know the formula, try to understand that when the formula is applicable or valid and when we should not apply a given formula. Once you realize that part, this chapter will be actually easy. So let me draw a large number of paraxial rays. I mean, sorry, rays, not paraxial. One coming at the top. The marginal rays will intersect the principal axis nearer or farther. Can you understand? If you draw the marginal rays, the farthest from the center, I mean principal axis, what you expect? This is the biggest angle,
Yes.
so the light will reflect like this. Isn't it?
Yes.
So let's draw multiple beams by drawing closer and closer. One, two. I will draw few lines. Okay. So let me do like all the normals, like how many normals you can do. Let me try this. Normal, 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 normal. And principal axis itself is normal to the mirror, right? Do you realize this?
Yes.
Principal axis itself is normal because it passes through the center. So any ray which passes through the center will be automatically normal. Okay, let me draw the reflection. This is fine. So you need to observe something, which I will draw here. As you come closer to the principal axis, the focus will shift, correct? And I think you can see some curve getting drawn because of the intersection. Can you see this curve? The curve is generated like this because of the point of intersection. This is called caustic curve. So you might have seen in the high school notebook. You can see this diagram is very common. It is actually like a more like a shape of a semicircle. Okay, so I cannot draw it exactly, but you can understand what I'm trying to achieve here. That even for a given incident ray, we can have infinite focus, and the focus will shift towards the or away from the pole. The longest focus, or you can say focal length, no? Longest focus. The longest focal length will be achieved for the principal paraxial rays. So paraxial rays will give you the longest focus or the biggest one. And in general, you can see for a given object, if the object is called the extended body, the entire shape will be distorted if you have a large mirror, large concave or large convex mirror. It will be highly distorted. So what we do is to make sure that the marginal do not show its effect, we cover the most part of the mirror with black paint, and only we let the central part exposed to the light ray. And if you cover the most of the part of the mirror and if you let only the central part exposed, then by default whatever ray will hit the mirror will become paraxial, no matter how they are hitting.
Sir,
Yes.
so can you repeat this part of it?
Yeah. So to make sure that we do not deal with the marginal rays, what are the solutions? Solution is you make a very small size mirror, like a small patch. And if you have a small patch size mirror, then the principal axis will be anyway close to everything, the entire mirror. In such case, even the marginal will behave as paraxial, isn't it?
Yes.
There are two ways. Either you make the size of the mirror really small, or if a big mirror is given to you, you can paint it black, like paint the half portion.
Yes, understood.
You just simply paint it. I mean, let's say the light cannot reflect from this part. So paint it black. And what you do, you let the small portion exposed. By doing this, you make sure that the mirror will be behaving only, or we will only creating the image for the paraxial rays by default with no choice left. And why such action is necessary? If you do not do, then you will get a blur images, and blur images is something which we definitely avoid. Therefore, all the formula which you study in a geometrical optics are only derived for the paraxial rays. The moment you see a question by JEE in which the paraxial approximation is violated, if they mention it explicitly, don't assume yourself. In such case, you need to re-derive the formula. Like we derive the formula for the focus, focal length. Okay. So that is the idea. And by making paraxial, we make sure that we have a unique focus, because if you take the beam very close already, then of course they will also have different focus, but these will be very close to each other, so the gap will be insignificant and we can treat such object as point object. So the whole idea is, if we have a a spherical mirror, then a parallel beam will create unique focus if the beam is paraxial. And to get rid of this issue of the spherical mirror, so large size spherical mirrors are not good to focus the rays at principal axis. They are very bad. So this is called the spherical aberration. So spherical mirrors are not able to focus a beam of light at one particular point. So this is called, so the phenomena of, what do you call it? Phenomena of infinite foci due to large size mirrors is called large size spherical mirror is called spherical aberration. Aberration, I always get incorrect. Aberration. You can just check whether it is A double B or A double R. I mean, I'm always confused with this word. So the phenomena of infinite foci due to large size spherical mirror is called spherical aberration. So if you really want to get the parallel beam getting focused at a point, which mirror we should use?
Small size.
No, we should use the parabolic mirrors. I have explained why. Only the parabolic mirrors having the property that whatever be the parallel beam, it will be focused at one point. Why? Because in case of parabola, there are two foci, one near, other at infinity. If you remember, and other is infinity. So it means any beam or any ray coming from infinity, no matter where it is hitting, whether it's marginal or paraxial, because infinity is the other foci. So this focus is the conjugate point, right? So this will go like this. This will go like this. This will go like this. No matter how you do, this will go like this. So parabolic mirrors can converge everything, no matter what's the shape, whether it's a big shape or a small shape. So most of the dish antenna which you install for your streaming, whether it's Airtel, Tata, whatever, I don't know how many brands are there nowadays. So all the discs are actually parabolic reflectors. And you must have seen, if you buy any antenna, a parabolic reflector, you must have seen something like this attached to the center. This is exactly the focus, and any beam coming, let's say you are receiving the signal from the broadcaster, all will go to this device, no matter how they come. And that is how we receive the signal. Okay. So parabolic reflectors are the way to go, or way to design the large size reflectors. So whether you want to create the antenna or any big radar, the shape is bound to be parabolic. So we design parabolic surfaces And designing parabolic surfaces at a large scale is quite a challenge because it's a completely geometrical construct you need to think about, or drawing a plot and then implementing in a real life is very, very challenging. So China had made one big parabolic reflector, which I think recently got destroyed. It's a huge, like a size of a football ground, to catch the alien signal. Like, and they have received a lot of signal from the distant galaxy and so many things. So anyway, the idea is spherical aberration you cannot avoid. Of course, if you want to want to create a converging rays for the large size, you have to deal with the aberration. So either you reduce the size or you switch to the parabolic mirrors. But of course, our job is here to study the spherical mirror, and so we'll stick to the spherical mirror. So after the primary focus, the next concept is what is secondary foci, and I use the word foci intentionally because the secondary foci is not going to be unique, rather it will be infinite. So this concept is again, let's see how it goes. So if we have a mirror, okay, now onwards, so secondary foci we define only for the paraxial rays. We are not going to define for marginal anything. Define for paraxial. So when we define the secondary foci, a beam of light which is paraxial. So the first rule is simple: the beam must be paraxial or light. So beam is a collection of rays. So I am just showing you one ray, but I will show you other rays also. So if beam is hitting this mirror at focus, at pole of the mirror, just a moment, let me do this. Uh, so if a beam is hitting the mirror at point P, the principal axis itself is normal, isn't it? It's normal. I hope you understand this part.
Yes, sir.
And if this is normal, then this is the angle of incidence. Let's call it alpha. So what will be the angle of reflection? So angle of reflection will be same alpha, isn't it? If alpha is the angle of incidence, then alpha will be the angle of reflection. Is this clear, guys?
Yes, sir.
Now what I said that we don't have one beam, one ray, we have a beam. So it means take one ray just above with no gap, and of course I'm showing it like this, and take one ray just below. Now how they will create the image formation? So we know the primary focus. Okay, we know the primary focus, and the primary focus we obtain for the parallel beam, a beam which is parallel to the principal axis. Now we have a beam which is tilted, and therefore what will happen if I call this as primary focus? If the beam was not tilted, if alpha was 0, then all the ray would have converged at F. A tilt will make sure that it will converge, but not on the principal axis, but off the principal axis. Off means somewhere here, which means the light ray, this ray will come here, and this will also come. So convergence will take place, of course, in the plane of focus, but not on the axis. So when we have the convergence of incident beam, not on the focus, what we call secondary foci. So this point is called this called FS. This is called secondary foci. But this secondary focus can be in any direction, in any circle. Like this is like a radius. If you move around this circle, because the beam can turn around the peninsular axis anywhere, you can think as a cone of incidence, correct? If a beam is
So
having,
like 360-degree around the principal axis.
yeah, correct. Because beam of alpha angle can be anywhere in the 360-degree, right? Do you realize this? No. Yes.
Yes, understood.
It's like a axis. We can have a beam coming from this angle alpha in any direction like this at any angle of cone. So the focus can be anywhere around the axis in 360-degree, and therefore it defines something called focal plane. So there is a concept of focal plane. And what is focal plane? It is the plane which contains all such secondary foci. So focal plane is a plane which contains all secondary foci. And the focal plane is always normal to the principal axis. Contains all secondary foci and is perpendicular to principal axis. So it will contain all secondary foci plus primary focus will be anywhere there, because if you contain secondary, primary is bound to there. So this is the plane, and because from distance from P to F is called F. So if I choose this as X axis, and if I call this as Y axis, and if I call this as the origin, what will be the coordinate of Fs? So coordinate, let me make it bold, of secondary focus, in this case, we can write as, you can see it's a simple formula. So you can see x coordinate will be minus f because it is always in the plane of f. So x coordinate is going to be minus f. What is the y value? So because of a small angle approximation, we can write tan alpha is the y coordinate, which is like radius. You can think this as radius of circle R. Radius upon f, you can write like this. So radius is how much? F tan alpha, correct? So y coordinate can be written as minus f tan alpha. Is this clear? Hello,
Yes.
am I audible, guys?
Yes, understood.
The concept of primary focus and secondary is clear. What is primary? Primary means the focus where the light ray converge. Which light ray? A beam, a parallel beam of light coming parallel to the pencil axis converges at a point on the pencil axis, that we call primary focus. A parallel beam of light not parallel to pencil axis will converge at a point in the focal plane of the mirror called secondary focus. Do I need to mention the definition? If you want, I can mention. So let me tell. I mean, you tell me what should I write here. Primary focus is what? A parallel beam coming parallel to principal axis converging at a okay, see it's not only about converging, it appears to be converging, but possible. Or it may be diverging from that point in case of convex mirror. So I am taking the definition for both scenario, concave mirror and convex mirror. So a parallel beam of a beam coming parallel to principal axis long, and after reflection it either converges or appear to be diverging from a point too much grammar, converges to a point or appear to be diverging from a point on the principal axis is called primary focus. That's too much of literature. It's totally mouthful. So of course you are not supposed to mug up this. I mean, I think you can get the basic idea. Definitions are difficult to create here. You can create, if you understand, you can write in your own words. But this is how we can understand. We can also do it for the convex. It's not only meant for the concave. And what we have defined, the secondary we have defined for the paraxial only. Why we only define for paraxial? Because marginal cannot have a same plane also. So the problem is every marginal will have its own plane. So it's like infinite plane, infinite focus, and everything infinite. So it's like the life will be like hell. So we cannot deal with the marginal rays and their behavior. So is spherical mirrors okay? Now the question is like how we understand that the given spherical mirror will behave in a nice way, even for the extended object. The answer is simple. Of course, while solving numerical, no matter what they write, we assume as paraxial. It's like a very crude hypothetical assumption with which we solve the numerical because there is no way out. But in reality, if you look at any foreign books, like foreign authors, when they write their books, they will mention the focal length in centimeter, but the object size they will mention in millimeter because they know that even the extended body should not be large enough. It should be few millimeter away from the principal axis. So given the radius of curvature in centimeter, let's say 100 centimeter or 50 centimeter, the 3 millimeter object is okay. That's totally on the axis. It's like even it's 3 millimeter, but we can assume that is completely on the axis. And because of such assumption, the formula will have a little more accurate result than the reality. The deviation from the reality will not be much. But if you look at the Indian authors, I mean, they don't make them, their values don't make sense actually. I mean, they take the object size in 3 centimeter, focal length in 5 centimeter and 10 centimeter, and they will tell you, okay, draw the diagram. The problem is, even the JEE is doing the same mistake. But nevertheless, if nothing is mentioned, you are supposed to think everything is correct. You're supposed to think that everything is close to the principal axis. I mean, no matter what dimension they mention. Okay. You are supposed to think. Am I audible, guys? I think I'm not
Yes, sir.
audible.
Yeah, sir.
Okay. Good. So I hope the concept of basic definitions are clear. Like the focus is the only thing which we do not define geometrically, we define optically. So focus or focal length is an optical definition. Like it is defined in terms of light ray, not in the terms only of the shape of the object. Okay. So you need to be very careful what we mean by focus. Center of curvature, radius of curvature, pole, aperture, these all are geometric construct. It has nothing to do with the light. We never involve the light in those definitions. The moment I say focus or focal length, then it depends on where the light is hitting the mirror, how far from the principal axis, and the moment we make the paraxial approximation, things become quite simpler, and therefore we are able to write the answers in terms of some variables. Okay. Otherwise, things will be really complex, and we won't be able to write anything. Is this clear?
Yes.
So all our derivations, until I am not giving you the dimension the way I gave for uh, the focal length derivation, f equals to. So this is the in general. This is like a one beam. This focal length formula is for one particular beam hitting the mirror at theta angle, correct? And what I
Yes,
said
sir.
for paraxial,
R by 2.
theta tends to 0. Therefore, f tends to r by 2. So this is like an approximation scenario. This is not the result that we can always apply, and so you need to be careful. If they show you that the light ray is hitting the mirror at angle 60 degree, don't use the r by 2 formula for sure. Go to the exact formula and then solve it. So I hope this is clear part. This part is clear. I mean, if you have doubt, you can ask.
No, sir, clear.
Okay, the image formation I will not take much because I know you guys can do it effectively. So I'll directly go to the mirror formula and its derivation. Or you want to see that image formation? Okay, let me show you. I mean, some quick. So in case of convex mirror, how many images we have? Okay, I show the image function. Okay, let me move this. Maybe something more insight we can get. Image formation due to spherical mirrors. Again, only for paraxial approximation. I cannot draw for the in general. It will be really blurred and complex and distorted, which I cannot. So you can start with concave is nice. Concave will have many cases. Concave mirror. So what do you mean by concave mirror? The inner surface is reflecting, correct?
Yes, sir.
So I will do every diagram in the same. Like just I will explain, and if you understand, it's really good. If you don't, then you can go back to high school and check the diagram. I'll give you some glimpse of how to think about it. Okay, so we always take the object. So we at F and then we have C, And because for paraxial F is exactly at the midway, because it's R by 2, so we can draw something like this. P and C, and in the midway draw F. That's how we start. So there are three cases, I mean, maybe four cases you can take. When the object is coming from infinity. Infinity means a distant object. So how we think about infinity? Any distance which is much bigger than focal length is called infinity. So if the distance of object is even 10 times than the focus of focal length, you can treat such distance as infinity. 10 times, yeah. So if I say the focal length is 5 centimeter, even the 50 centimeter is like a infinity. So generally, infinity is the idea. And the idea that you need to remember is that any light ray coming from the distant object or the infinity, let's say light ray coming from the sun, star, moon, or any planet after reflection, whatever light ray we receive from the heaven, or heavenly, not heaven, because from the cosmic world, all such rays are paraxial by definition. So the rule which you must remember, as a note I can add, any ray coming from distant object is always taken as paraxial. So paraxial does not mean parallel to the principal axis. It could be parallel, it could be tilted also. So you may get primary focus, you may get secondary focus, but that is the assumption. Okay. So for the sake of drawing, I'm just taking some paraxial B. Assuming the mirror size is small enough, I am forcing myself to think that these are small. So these rays are coming from quite far object, and by definition, any light ray which is parallel to the principal axis will pass through the focus. That is how we define the focus in the very beginning itself. It is not like that the light ray will pass focus. It is how the focus is defined. It means the point where the light ray will converge is the focus. So that's the property. And as I said, light ray follows the principle of reversibility of light. So if the object at infinity, you can think like there is some hypothetical object kept somewhere here at infinity, which forms the image. And what you can write that the light ray from the tip goes down and the tail goes up. So you can see the tip and tail will get inverted, right? Because they reverse the direction after reflection. And because of the reversal of direction of the tip and the bottom, we say the image will be inverted. That is why we say the image form will be inverted. Because they actually intersect, we call it real. And at F, because any parallel beam will meet at a point definitely at F. So it could be at F in the focal plane also. Need not to be exactly in the principal axis. But no matter which part of the plane you choose, your longitudinal distance from the pole of mirror will be F1. So longitudinal distance is called the distance measured along the axis.
+918356820.
Okay. So the first part is clear. Image will be real. Why? Because the light ray is actually intersecting. It will be inverted because the top going bottom and bottom going top, reversing the direction. And third is at F. And fourth is highly diminished. You can see that even the infinitely large object will become a point object. Is this clear? Yes or no? Hello, hello, hello.
Yes, sir.
So this is the first part. I mean, of course, if you want to explain, you can explain in your own words. Should I explain here? Real inverted highly diminished at F. Okay. But at F is even not a very right answer. I mean, of course, till class 10, that's clear. What we say is in focal plane. But that's it. The at F means the longitudinal distance is at F. That's right. Okay. So now comes the interesting point. Let's say if you have a concave mirror, there's a very famous question which I would like to take here. Let's say we have a concave mirror. Okay. So let's say we talk about sun. How far is sun? At infinity, but not exactly infinity. Even we know the distance. So sun is at one astronomical distance away from the earth, right?
Yes.
So let's say this is the giant sun, and the bottom of the sun I'm taking at the principal axis and the top at some distance away. And this is the diameter of sun. See how we find the dimension of heavenly bodies. This is the diameter of sun. Or knowing the dimension, we can find the distance and so on. So what happens? The light ray from the tip of the so the beam emanating from this portion and because it's coming from the infinity, it's must be paraxial. So what we get is not just one ray, of course, and we are getting infinite rays. So we just need 3 points, even 2 points sufficient from the image. Just Okay, sorry guys. Am I audible, guys? Hello, hello, hello.
Yes, sir.
Yes, sir.
Now you can see that if a beam is coming from the top of the sun, this is sun, and the beam will come and will get focus at the, of course, in the focal plane actually, because this is the secondary foci. So this point is like a secondary foci, correct? And the beam which will come from the bottom will be exactly here, primary focus. Do you realize this fact? So if I just take the end position and if I draw few lines, few rays from there, we can exactly find the location of their convergence. Do you realize this?
Yes.
Yes. Sir. And from the laws of reflection, can we say this angle must be same as this angle? Can we say? So if I take the distance of sun from the earth as s, because that's exactly the distance from the mirror from the sun, because we are on the earth. Can we write it tan theta? Because that's very easy. Or you can write just theta. And you can take this as the arc length, the size of the image of sun and the actual size of sun, you can take as arc length. So d upon s, I hope you can understand, is same as small d upon f. Do you realize this? No. This is f. So d upon s is equals to small d upon capital F, I mean small f, correct? So the image size, we can go get it. So how big the image of the sun will look like? Now, given the distance of sun and all, you can find the small d. So this is a very famous question. Finding the size of image of sun. Finding the size of image. Anybody having any difficulty in realizing this part?
No.
And if you like if you extend this light ray further, you can see it. If you put an eye here, you can see the image of sun. So that is how the reflecting telescope works. So if we talk about the telescope, the other telescopes like Galilean and the astronomical telescopes are quite heavy and expensive in terms of manufacturing. In the old days, of course, we have made some observatory with such big lenses, which are very difficult to even manipulate. So heavy, because imagine a glass size. Uh, if you think of glass, if you create a glass of size of football, I think it's very difficult to manipulate. It's so heavy. So later on, they invented the reflecting telescope to do the same analysis. Okay. And to create a better image, the aperture is very important, whether it's a lens or mirror. So whenever we try to create telescope, we try to make the aperture as large as possible so that we can get the maximum exposure, and more the light ray coming, because anything anyway the light coming from a distant object is very small. A big aperture will make sure that somewhat we get a good image. And now the modern telescopes are using the extreme technological advancement like machine learning and the neural network to regenerate the image. Once they receive some image, they pre-process it, and then they generate even more, you can say, astonishing images. I mean, they are doing superb job. Okay. And if you remember that the black hole image is itself the biggest achievement in the world of technological advancement. So the lady who captured the black hole, what she did was same thing. She received images in bits and pieces over the years, and she digitally combined all such images to recreate the black book. So modern digital telescopes are very powerful in terms of pre-processing and creating the accuracy. I mean, accurate image. Anyway, so maybe that will be used in by future. I mean, in future by some other uh, application as well. The next part. Okay, we are doing the image formation due to the concave mirror. We saw one thing, the parallel beam. Let's go to the regular motion. Right? A beam which is not parallel. So let's say we have a mirror and this is too much. So after infinity, like infinity means the distance is quite away, like quite far, much bigger than the focal length. Now the next case will be when the object is not at infinity, rather it's close to the or in between the infinity and center of curvature. So how we denote such object? We put it somewhere here, something like this. You can take extended body also. I'm taking always point object because that gives you the better idea. So how the image is formed? We need at least two lighters. I will show the two lighters, one going like this. Now, if you draw the normal at the point of incidence, because that is what we need to do, then only you can think about the laws of reflection. If this is the normal, this is the incident ray, this is the angle of incidence. So what do you think? What will be the angle of reflection? The angle of reflection will be same angle like this. You can see. Hello guys, am I audible?
Seriously.
So if the angle of incidence is known to you, can you see the angle of reflection?
Yes.
Now you can animate this image in your brain. And how you can animate? As O will approach towards the C, this reflected ray will come closer to which point? C or F? As O will approach C, I will decrease. Do you realize this? Hmm?
Oh, yes, sir.
And as I will decrease, the reflected ray will move towards which point? C
F.
or F?
F.
Hmm? Very good. Excellent. As I will decrease, the image will shift towards F. Very good.
Sir, C, sorry. Then it will shift towards the north. C.
Yeah, of course, if I will decrease, the reflection angle will also decrease. So it will be almost converging with the C line,
Yes, sir.
isn't it? Like you need to imagine, see, create the imagination. As O will come closer, the I will come closer to the normal. So when O will be at C, the light will just reflect back here.
Yes, sir.
And the moment you cross the C, if the object will go on the right of the C, the light ray will go this side. And the moment the object will reach the F, the light will become horizontal. Why? Principle of a reversibility of light. If you interchange the position of object with image, the light ray will retrace the path. This is the condition when the object is at F. And the moment you cross the F, the light ray will be diverging. So the image will be on the right hand side, the virtual image. Once again, look at the animation. So you start from here, infinity. and then you approach towards the center, light ray will shift like this, like this, like this, like this, like this. Imagine the animation. Now I cannot take two light rays and show you. I have the liberty of using only one movement. And when you reach the C, the light ray becomes exactly like this. Because any light ray going from C will reflect back. Because it's a normal ray. It's called normal incidence on the mirror, right? But the moment the object will cross on the right side of C, the light ray will hit the mirror from other side. So it will go this way. Do you realize this part?
Yes.
And then as the object will reach the focus, the light ray will go at F. So image will go to infinity. And once you cross F, what will happen? Once you cross F, there you start getting the which image? Virtual image, because it is not diverging. The reflected rays are diverging, and any ray which is diverging cannot create the real image, isn't it?
Yes.
Because they will never meet.
The real image.
No, no, virtual image. No.
Yeah.
Once you cross, once the rays are diverging, we cannot get the real image. This is what I'm saying. You won't get the real image. So what will you get? Virtual image.
Virtual image.
And the image will be on the back side, of course. So I mean, this takes care of everything. You can just do the mental animation and you can imagine what is happening. So once the object crosses the C point, the reflected light will cross the C on the left. Okay, so it's like they merge at C and then they reverse the direction. So O goes beyond C, I goes beyond C in the opposite direction always. Okay. Now the special case is what happens if you cross F. So at F you are becoming parallel to the principal axis because of the principle of reversibility of light. So the moment you cross F, you start diverging. And for the obvious reason, let's say you take any point, take any point. You choose any point. If the object is here, the incident ray will change. Na? How the incident ray will look like? This is the incident ray, and you can see it's a really huge angle with respect to normal. So how the light ray will go? At the same angle this side. Can you see that?
Yes.
And therefore this light ray will go this way, and if I choose one more such light rays, or if I extend this backward, and this light ray will just reflect back, so these two will intersect somewhere here. So image will be virtual because these two light ray will never meet, but they appear to be coming from I dash. So that's why this is called the virtual image. And what you can realize that the top will go up and the bottom will go bottom only, so it means the image will be erect. It's not inverted. With the object, it's not inverted. So if you think of a tiny object like this, a small tiny, the tip will go up and the bottom will go down. And therefore these rays are, the up is up, the down is down, it means no inversion. I hope this is clear. The
Yes.
no inversion condition. So this is how you can imagine the ray diagram for the concave mirror. Now, so far, the object I have considered was a real object. So one more special case that we need to consider is the what happens if the object is what I mean virtual. Okay. So let's take the case when the object itself is virtual. So this is the point P. Okay. So we'll take the one special case that if the incident ray, look at this guy. Am I audible, guys?
Yes, sir.
So what if the incident ray itself is converging? Ray is coming like this.
So the purple.
The ray is coming this way. Just a second. So if the incident ray is converging like this, what will happen? After reflection, the light ray will come like this. So if I choose one more symmetrically, or if I choose one light ray along the principal axis itself, so these two will intersect at which point you can see clearly they will intersect here actually.
Yes, sir.
Now, is this image real or virtual?
So real image.
Yeah. It means concave mirror. Okay, and this object is what, real or virtual?
Uh, is so
It's
virtual.
virtual because
So
it's a
because it is not
yeah,
actually meeting.
yeah. If you look at the incident rays and if you trace back, they will never meet in the actual direction. So you need to produce forward to meet them. So it's a virtual object. What you need to realize that virtual object also creates a real image. So what concave is capable of? It is capable of creating virtual image of real object, real image of real object. So real to real possible? Yes. Real to virtual possible? Yes. You
Yes.
can see, because if this is the virtual image, this is a real object. So real to real is possible, real to virtual is possible, virtual to real is possible.
Yes.
The only thing which is not possible is virtual to virtual. We cannot create a virtual image of virtual object in case of concave mirror, no matter what, how you keep the object. And that is obvious from the ray diagram. You can realize that everything is possible by the concave mirror, but concave mirror cannot create the virtual versus virtual. The rest it can create. And to master this concept, you need to draw. You see, at home, you make sure that you do enough practice of the ray diagram to realize what is happening. Always do the normal and do it manual. Just take a pencil and paper and try to go through all the possibility using the laws of reflection. And always play with this. I mean, you should spend some time doing this just to get the intuition. So concave mirror can form everything except the virtual condition. Everything is possible. So this is the end of the concave mirror. We can go to the convex mirror. The extended body, I will not take right now. Maybe while deriving something, if I need, I can take, or I will take. Okay. So the next part, convex image formation due to convex mirror. Okay. So image formation due to convex mirror. And what we can say? So if we have a convex mirror, oh, this time I have to change. Convex. Now, in this case, the center of curvature is on the right side. That's the problem. So if you want to draw a normal, you have to draw like this one. There is no option. And but the object we are going to always keep on this side, no? Okay. So we'll take two cases. One, if the light is coming from infinity. If the light ray is coming from infinity, it must be okay. We can take as parallel beam. So we will take the parallel to the principal axis scenario. You have the normal, you have the incident ray. Can you see the angle of incidence?
Yes.
Yes, sir.
And if you can see the angle of incidence, how the light ray will go after reflection, up or down?
Up.
So one thing is clear, that is this will always diverge, isn't it?
Yeah, sir. Yeah.
If you take even any other light ray, it will only diverge, correct? Which makes sure
Yes, sir.
that the image is bound to be what?
Virtual.
Virtual, correct? You can take one more light ray, but I know that if I take one light ray along the principal axis, it will just reflect back and the ends will meet like this. So we can say this is a virtual image of the real object. Although the object is at infinity, but it's a real. So till parallel we consider real. Of course, the if the incident beam is eventually converges backward, so we call it real. But we even the parallel we take as real. So we have real object and what we have virtual image. Now take the other cases, or you can do the same thing. Okay, and this point will be what? This must be by definition f, and you can see it's half of the C and P.
Yes, sir.
But you can also realize that if the primary focus of convex is on the right side, earlier it used to be on the left
Left
side.
side.
So what we need to realize that the incident ray, since the incident ray is towards the right, and if you look at the focus with respect to pole, thinking pole as the origin, and if you see the f, you will see like this. And what you can realize that the direction of incident beam and direction of this arrow is same. In such scenario, we take focal length as positive in formula, like when we learn the sign convention, this will be helpful to you. So if the, see, if we measure everything from the pole, so anything which we measure along the incident ray we take as positive, but you need to see things from pole. And here, if you look anything from pole, it will be left. So every term, whether it's focus or center of curvature or object, everything is on the left. Whereas the light ray is coming from the left to right. So that's why it is always opposite in sign. So we take negative values while solving. Of course, you can have any convention, but that is how we take the convention. So we'll talk about the convention later on when we do the mirror formula derivation. The other scenario is what? We have taken one scenario, let's take the other scenario. So we have a convex mirror. So we have a convex mirror, and what you can see, the object. Okay, and it's always good idea to always do the normal before you draw the any ray diagram. So the normal is going from center to any point on the mirror. That's normal by definition of circle, right? So now knowing the normal, choose any point on the principal axis. Any point. It really doesn't matter now whether it's close or far. Okay. So take any object. How the light ray will go from this object? This is the incident ray, correct? The reflector ray will be like this. Do you realize? And therefore, so this is the primary, sorry, this is the image. The focus is exactly somewhere here. So the moment you bring the object like this, what I can say? The image is still virtual, no effect because it's still diverging. Angle of incidence, angle of reflection, both are right. So the reflected ray, no matter where you are, the where you take the object, is going to be diverging. So image is always virtual. So every real object will only create. So real always creates virtual, correct? So what else you can create? Object, image. We create real to virtual. Let's talk about the virtual objects because that is rarely discussed. Of course, in high school we never discuss. Now we need to discuss. Now we are going to make the object itself virtual. And for making virtual object, what we need to do? We need to make the incident ray converging, something like this, correct? The ray is coming this way. You want to draw, you can do more lines, but it really doesn't matter. So if these are the incident ray, if you trace it back, will they meet? The answer is no. Oh, that's interesting. My object is hitting the center itself. It's an These are normal rays, so it will just reflect back, isn't it? It will just come back. I mean, of course, this happened by chance. Okay, I was not intending to do this. So the ray will come and will go away in the same path because it's a passing through the center of curvature. So these rays are essentially hitting the mirror at right angle, and whenever the light ray will hit at right angle, what will happen? The retracing of path. That's very important. I am doing it intentionally because you need to understand that the light ray can retrace only when they hit at right angle, whether it's plane mirror or a spherical mirror or even a parabolic mirror or any sinusoidal mirror or any mirror in the world. Any incident which is at right angle to the surface of mirror will let the ray to retrace. So it will go back to the same point. Now tell me, the object is virtual,
Yeah. Yes, sir.
but image is also here only. No? Image is also here. Because if you trace the reflected light, it will also appear to be coming from here. Why?
Sir, I didn't understand virtual.
What is
Oh,
the meaning
yes,
of
sir, understood. Yeah.
see the if the object is at C, the image must be at C. Okay.
Yes, sir.
And here the object is virtual because the incident ray is converging, and our image is virtual because the reflected is diverging. So you cannot trace any one. If you try to trace the reflected ray in its path, will it ever meet? No. If you trace back the reflected light, will it meet this one? Are they going to meet? You need to move it backward, huh? Produce backward. This light ray will never meet, na? So what will do? You will produce it backward. So what will get? A virtual image. And the incident one, the incident one, you can see these two incident one. If you trace it back, they will also not meet. This is virtual object and virtual image. So what do you realize? The convex mirror is capable of creating
Virtual.
virtue, which was not possible in the previous case. And you will very soon realize that what is not possible here. Here, real forms virtual, virtual forms virtual. So, what is not possible? The real to real is not possible. We cannot have
Oh,
the
yeah.
real to real. So, in concave, virtual to virtual is not possible. In convex, real to real is not possible. So, one question is left that can we have the virtual to real? So, can we create some, example in which it is possible? The answer is yes, very much we can. And that's the property of uh, convex mirror. And I can just show you here only. Any light ray which is hitting the mirror above the normal, like somewhere here, because fortunately this is normal. If the incident ray itself is above the normal, the object is still virtual. You can see the object is virtual for sure. but the light ray after reflection will go down. Can you see that? You can see, and therefore there is an intersection of this pencil axis with this point, which will definitely the image position. And the image is what? Real. Do you realize this? That image is real.
Yes, sir.
So what do you realize? That in case of convex mirror, all possible ray diagrams are like there, except one possibility is not there, which is real to.
Real.
Yeah, sir.
You cannot have the real image of real object in case of convex mirror.
Convex.
In case of concave mirror, what is not possible? Virtual to virtual. Concave cannot form the virtual image of virtual object. Do you
Yes, sir.
realize it?
Yeah.
And the last is plane mirror. So plane forms real, virtual, real. What is not possible? Neither real to real is possible, nor virtual to virtual is possible. For which mirror? Plane mirror. Is this clear? So you can make a summary table that what is possible and what is not possible if you want. I can do quickly. So the table for 3 mirrors. Yeah. So type of mirror, and there are 4 varieties. 1, 2, 3, and 4. Yeah, I think. And we have 3 types of mirrors. So let me make 3 verticals. 1, 2, 3. Done. On what we can write here? Plane mirror. Then which mirror? Concave mirror. Convex mirror. Okay. So the plane mirror is what? What is possible? So what I can do is I can make one more table of real, virtual, like this, and then we can just put a like tick mark, possible or not possible. Yeah, that's also nice. 1, 2, 3, and okay, I think I can make one more point here. Object type image type. So I'll start with real, virtual, real, 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 virtual, virtual. Okay, and that's I will make a tick. So plane can form real to real. Real to virtual, correct. Virtual to real, correct. This not possible. Concave, yes, 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 no. Convex, real to virtual, yes. Virtual to real, yes. Real, no. And virtual. This summarizes everything. Am I audible, guys?
Yes, sir.
So now we are done with the image formation. I hope you got the basic idea that how images are formed and how one should approach the image diagram, like how you should draw the rays, how to draw the normal, and do the rest of the stuff. Okay. So in case of mirror, if a light ray is parallel, it will pass through focus. If the light will pass through focus, it will become parallel. Why? Principle of reversibility. Okay. The principal axis itself is normal to the mirror. So the angle of incidence of a beam with principal axis becomes the angle of incidence, and therefore the angle of reflection will be same. What is this? Is what I used to derive the this example. Understood? So any angle of incidence at the pole is the, or you can see the angle made by the beam with principal axis is the angle of incidence also. So this is I. This is R. So why? Because the principal axis is always normal to the mirror. That's the reason. So these ideas you have to keep in mind while attempting numericals. Practice as much as possible the ray diagram. Play with it. Try to realize what is possible, what is not possible. Draw always all possible scenarios. Think about more of the virtual objects than the regular question which you see only the real objects. And practice these ray diagrams at home. Then you can get some insight like how to think about it. So what next? So of course we have something like called like sign convention. Okay, if I want that. All right, sign convention. So there are many conventions. One is called the Cartesian convention. So you choose one direction as positive, the other becomes negative. But I will tell you like what is the better way of making the convention. So for any given mirror, you can understand easily that from which direction the light ray can come. So if I have a mirror like this, from which direction light ray can come? Left to right. Common sense. From which direction the light ray can come? A or B?
A. So from which direction light ray can?
Light ray can come and hit the mirror. So for this case, what is the answer?
A.
Common sense. That's A, right? For this case, second case here, from which direction light ray can come? Hmm? No idea.
A.
Of course, A. Here,
A.
A. A can come. Here,
Sir, in second case.
yeah. A, of course, here A and A. Correct. In the rest two cases here,
Third case B. And fourth case A.
A. This is the polished surface. How light ray will come here? Light ray always comes on the reflecting surface. No?
So third case B and fourth case B.
Oh, this is same. Oh, I drew the same diagram. Oh, my bad. I made the same diagram. I should have drawn something like this. Anyway, so the whole idea is you should be able to understand from which direction light ray can come. Okay. So for a given mirror at any, just think of any mirror. You can choose anywhere concave or convex, whatever you want to choose. So always draw the principal axis before you draw the convention. So this is, let's say, principal axis will be like this, and the pole you can think as origin matrix. So always take the origin at pole. Now how the light ray can come? This side or this side? Up or down? Light ray can come from which side? Up or down? Hmm?
Up.
Up only. Only up, right? So always take the possible direction of incident ray as the x-axis. So I will take this direction as x-axis. Always. So always take the direction of incident ray as x-axis. Now you also need to do the y-axis near the pole. That's, there is no restriction. You can draw either this way or you can draw this way. Choose whatever you want. It doesn't matter. So I'm taking this way. So if you do a perpendicular, this is y-axis. So if the object you keep somewhere here, then, or you can keep the object here also, or you can keep here also, you can keep anywhere. So you can keep object at any distance, at any location. So it is not necessary that we must keep the object on the principal axis. We can keep the object even off the axis. Okay. So we will have two coordinates. One is called the x and other is called the y coordinate. So let's say I'm taking some random location here. So I need to draw a perpendicular to get some y height. Let's go, this is h. And what will be this? The coordinate of the bottom. Let's say the distance is d between the bottom and the O. So what will be the coordinate of bottom? Minus g comma 0. X-axis is that way, so this is minus g, correct? So what is the coordinate of object? If this part is not clear, let me know. It is clear.
Yes.
So do you realize the coordinate of object and the bottom and everything else?
Yes.
Now what is called d? D is called longitudinal distance of object from pole of mirror. What is called h? Transverse distance of object from principal axis. So how far is the object from the principal axis is called transverse distance, and how far is the object from the pole along the principal axis is called longitudinal distance. So when you studied the mirror formula, 1 by u plus 1 by v equals to 1 by f in class 10, what was the u and v representing? Object distance. What u is called? Object distance or something else? What do we call?
Object distance
And v is called? V is called what?
is distance.
Right? Now what was the mistake? guys, am I audible? 1 2 3 1 2 3.
Yes, sir,
Hello,
you're
hello,
audible.
hello, hello. Okay. So now we can do the derivation of mirror formula. So in mirror formula, what we try to achieve? In mirror formula, what we try to achieve? The relationship between the longitudinal distances, right? So mirror formula is all about relating the longitudinal distance, not the actual distance or the transverse, only the longitudinal. So we can derive it for any mirror. You can take whatever you want and learn the derivation very carefully, because only those who understand derivation in geometrical optics, they can actually solve any question with ease without getting confused. So once you know derivation, you know how to manipulate things in a difficult situation. So let's say we have a one A mirror to begin with of focal length f. When we derive formula, then the formula should be independent of mirror, but we have to choose one of them. So we use the proper sign convention even with the symbols to get rid of the mirror type. So let's say this is f. Take the real scenario, take the object is somewhere here. And the first step of solving question is drawing the normal to the mirror. Can you draw the normal? I hope by this time you are expert of drawing normal. How I should draw the normal here? Tell me. Anybody there? Hello guys.
Yes, sir.
How to draw the normal? Tell me. How to draw normal? Okay, how will you draw normal? Tell me. You how you are going to draw the normal here? No idea.
Sir, how to draw means like normal.
Yeah, on the mirror. Simply by drawing the so draw any line from center of
Sir,
curvature
but
that will
first we
come from.
need a line for drawing the normal.
So any line which you draw from center of curvature will be normal to the mirror, no matter where you draw.
Yes, sir.
And of course, we're taking the parallax. So my ray is something like this. But if I draw something like this, I cannot demonstrate. So what I'll do, I'll take something bigger, and we'll take the approximation later on. Okay. The next part is so this is the angle of, let's call incidence I. So as per the laws of reflection, this ray will come back like this. and we can call the angle of reflection, which is also I, correct? And this is exactly where the image will be formed. So we know the I now. This is the P, the pole. Okay. So how we begin solving question here? So we assume some angle. Let's say this is alpha, this is beta, and this is delta. I mean, you can take gamma also. I take delta and delta. So how to relate alpha, beta, delta? Tell me. How to relate alpha, beta, delta? What is the relation between alpha and beta in terms of I? So alpha plus I equals to beta. Do you realize this? And beta plus I equals to delta. If this part is clear, let me know. I think this is not clear. The exterior angle is equals to sum of the far interior angles. Last 10. So beta is the exterior angle of the alpha and I. Okay, I think you guys are not listening to me. So we can write I equals to beta minus alpha from here, and we can write I equals to. When we derive some formula, we want our answer to be independent of the angle of incidence. It should be same for all angles. So we must eliminate I, and which is clear. We can write as therefore beta minus alpha is delta minus beta. The next step is obvious. We can write alpha plus delta equals to 2 beta. And the next is again interesting because we do it for paraxial. So alpha, beta, delta, all are very small angles. So we can also write as tan alpha, tan delta is 2 tan beta. So you can convert the angle into tan. That's okay. And the P dash is for paraxial rays, the P dash will be coincide with P almost. So for paraxial approximation, and I should have written this before only. So for this is in general, this is in general. So till here we have no paraxial approximation. No paraxial approximation. So for paraxial approximation, we can convert this into tan, and then tan alpha you can write as h upon. You can take p dash as p for paraxial approximation, and so h upon and tan alpha is how much? P o. Yeah, that's correct. Tan delta is how much? Pi. And 2 tan beta is how much? Tell me guys. So beta is P.
Yes, sir, PC.
So we get the relation 1 upon PO plus 1 upon PI is 2 upon PC. Now what we do is we substitute the symbols, but even to substitute the symbol, we use the sign convention. So PO, P to O, PO is called the object distance along the principal axis, we call it U. And because it is against the incident ray, because our x axis will be like this. Let me go the other axis. This will be your y axis, this is the origin. So the U will be with minus sign because it's going to be negative. So we can replace PO by minus U. Can we replace PI by minus B? And can we replace PC by minus R because everything is negative on the left side of the origin? So this gives the formula 1 by U plus 1 by V. is 2 by r, and we know 2 by r is called what? 1 by f. So that is how you get the so this is the basically I mean this notation was used by the Britishers. So most of the British authors they use this UV convention. Americans never use this. So what they do, they use the x value, x not xi. So they write as xo, xi, and I think this is better one. UV is confused. So they make sure that we are doing the x coordinate relation. So this is the American convention. This is the British. So in different textbook, you will see these different notation, and they prefer the x notation to represent. So all right, this is the mirror formula. This is called mirror formula. And look at the derivation. It's pretty simple. Like we were able to derive because of the peripheral approximation only. And so you need to remember that how it is derived. And this is the very much the modus operandi of derivation of every question. So if you want to master the derivation in geometrical optics, you need to know how to draw the normal, how to draw the incident ray, a reflector ray. In the lens chapter, what we do, we replace the I and R in terms of Snell's law. So we write the Snell's law, and then from there we derive the uh, various formulas. The method remains almost same for derivation. So try to understand the derivation part. It will be really helpful to you. Okay. So I hope this part is clear to guys. Any doubt in this?
No, sir.
And why we put the sign with symbol? Because we wanted to get rid of the given mirror. So we derive using concave, but this formula is true for concave or convex or even plane mirror. How to find the plane mirror relation? Put f equals to infinity, you get the plane mirror. The answer will be u equals to minus v, which exactly happens if the u is negative, v will be positive and vice versa. I hope this is clear. So for plane mirror, the radius of curvature tends to infinity, and therefore the f will be also tends to infinity. So 1 by u plus 1 by v equals to 0. So v equals to minus u, which is exactly what plane mirror does. It forms the real to virtual and virtual to real. So if u is negative, v will be positive for sure. But if u itself is positive, v will be negative. So that's the interpretation which you can understand from the mirror form. So one more thing before I end today's lecture. In fact, I will finish this all derivation, then I'll end the lecture. So next is magnification. And one more formula. So we have to do something called the Newton's formula. So what is Newton's formula? What he did, instead of measuring the distance from the pole, he preferred measuring the distance from the focus. So that's the only difference. So I can write here. In this case, the object and the uh, image distances are measured with respect to focus than the pole. That's it. That's the only relation. And this makes equation really nice, and it helps you in solving question almost mentally without doing the rigorous calculation. I mean, anyway, it's not rigorous, to be honest. Easy calculation. You can just substitute U, V, and so on. Okay, so let's see how it will help doing things mentally. So what I'll do is again I'll keep the same convention. I'll keep F here and C here because I want to derive something. I will keep the object here only away from F. And we know if object is on the left of the C, the image must be on the right of the C, right? Somewhere here. I mean anywhere. So what is the distance of object from F? So we call this as xi. Sorry, xo is object. And the distance of image from the F is how much? Let's call it xi. And this distance is anywhere we know. If the focal length of mirror is F, this is actually F in length. So we have a mirror formula which says that 1 by U plus 1 by V equals to 1 by F. So we can substitute U as, what is U basically? Can you see? From the pole, what is the distance of object? F plus x naught with minus sign. I mean, of course, I'm writing the minus sign. Okay. And here F is the value, not the symbol, not the F. This F is symbol. That's why it's very confusing for students. They get confused between these two. When I take F here, this is the value. But when I'm writing F here, this is the symbol, which may be similar to value, which may be different from value. So that is a big point of confusion for many students. They
Sir,
get
how will
confused
it be
about,
different, but from well?
different in terms of sign. Symbol will have no sign. No? F is F.
Yeah, yeah.
But when you substitute as a value, you have to put sign also. F can be positive, can be negative, right? Let's say for convex, it's positive.
Yes,
For
sir. Yeah.
concave, it's a negative. So when you substitute symbol or replace symbol by a value which is looking similar to the symbol, that's very confusing. Whenever we replace a value, if I know F is the value, I will take care of symbol. If I know F is the symbol, I will never put the sign. I mean, if it is value, I have to take care of the sign. Value comes with sign. Symbol remains symbol. No sign to be used. Okay. So, okay, let's write a U. What is U we connect? U we connect is minus F plus x naught. I hope this is clear. And this F is value. I mean, just numerical value. What about the V part? Minus F plus xi. And what is the F part? Which is also minus F. Do you realize this? Because F is value, no? I'm writing it alone, so I have to write with sign.
Yes, sir.
That's very, very carefully have to be. So now we can take the LCM and minus we cancel out. So you can write F plus x naught into F plus xi F plus, oh, you can say 2F plus xi plus x naught is 1 by F. Let's multiply both sides. 2F square xi F plus x naught F equals to, and if you do this calculation, F square plus Fxi plus Fx naught plus F xi x naught. Yeah. This cancels. So xi into x naught is how much, you can see? Can you see this answer? And this answer is pretty easy because it's simply the product of distance from the focus is equals to f square. Isn't this easy to remember? This is called Newton's formula. Clear? Maybe.
Yes, sir.
Okay, so let me do some problem. And because see in class 10th you have used a lot of UV relation. You can also use this relation for question solving. If you know the distance clearly, you can just solve this easily. So let me show you some example in which you can realize why this is so interesting. So let's say we have a con so let's say we have an object which I know is at a distance of 20 centimeters, and I want to know the distance of image. I mean, for sure, I know the image is going to be real. Why? Because the object is beyond focus. So focus itself is how much? Only 8 away. So what is the distance of object from focus? 12 centimeters. So what is the formula? 12 into xi must be equal to f square. See, I got the answer. So it's 4, 3, and 16. So the u will be how much? The mod of u will be how much? The distance? 8 plus 16 by 3. Oh, you can do it like this. Do you realize? Sorry, this is v. My bad. The image distance will be how much? The image distance is 40 by 3 from the pole and 16 by 3 from the focus. Clear?
Yes.
Okay.
Yes, sir.
And then there's a rule also, like if the object and the image are on the two sides of the focal length, it will be one will be positive, other will be negative. Same side you can take as positive. So you have to be careful while using this relation, but it's really interesting. You can, if you want, you can solve more questions. Let's take something like 5 centimeter. An object is at let's say 10 centimeter. Just make it easy. So how to write here? Here the focus is on this side, right? And so the confusion will be there. So focus is this side, so you have to be knowing this answer. This is 5. So what is the XO? 15. Correct. What is XI? I don't know. So what you can write? 15 into XI equals to 25. XI is how much? And it is less than 5 for sure. It is 1/3 of here. So it must be somewhere here. We got that 5 by 3. If this is 5 by 3, this will be how much?
Call from +91835.
So if this is 5 by 3, you can find the distance from the pole. How much?
So 10 by
10 by 3. So you can verify using the formula which you know. So u is how much? Minus 10. You can take the x-axis and so on. And v will be how much? Along the incidence we take positive. So v I don't know. I'll keep it v as symbol because when you don't know anything, just write symbol. If I know it's going to be positive, so I will write 5. So 1 by v will be how much? 1 by 5 plus 1 by 10. LCM is 10, which is 3 by 10. So v is, and it's the positive answer, so it's on the right side. So you can see it's pretty easy to solve by both methods. I mean, of course, both methods is equally easy. This is effectively faster. I can do it mentally because I need to take the inverse summation. Inverse means you need to take LCM and then solve. Here the LCM is not required. That's the only benefit, and you can do pretty fast. I mean, if you practice a bit for a while, you can realize the power of this Newton's formula. Especially for mirror, you can go back to solve any question of class 10th. You can do most of the question mentally now using the Newton's formula. Of course, not of much use because JEE will never ask question of this easy difficulty, this level of easy or difficulty. It's pretty easy question. But of course, it may help you in doing the intermediate calculation of a tough question. So now I'll talk about the magnification. That's a very important concept. Magnification is a kind of meaningful term for the extended object. For a point-like object, the image is going to be point-like. So the magnification will make no sense actually. But if you have an extended object, things will change. Okay. So again, let's try to understand. First, okay, I'll define types of magnification. Then we'll do the derivation. So in ray optics, there are two types of magnification that we define. One is called the linear magnification. So we have something like linear. It is also called lateral. It is also called transverse. So linear or lateral or transverse all are same thing. The other is called longitudinal. That's unique. So longitudinal means the magnification along the axis. So if the object is not kept perpendicular to the axis, principal axis, rather it is lying along the axis, then what we get is called longitudinal magnification. Okay. And if it is kept perpendicular, so we call linear or transverse and so on. So let me draw this. So basically, magnification relates the transverse distance of objects. Even if I take a point object here, and If I draw a perpendicular, so this is called the height of object. So magnification is simply defined as the ratio of size of image upon size of object. That's it. But the size here refers to what? It could be anything. It could be transverse distance as size. It could be the longitudinal distance as size. So you can think size as the end points of the given object. And generally, we measure two things. One, how far is the object from the principal axis? If we have just point, then we just check the transverse distance. If we have the object, then we check the beginning of the object and the end of the object. We think like this. Anyway, so h naught is the size of the object. So if you have the transverse, if you have the single dot, so it cannot have the uh, longitudinal answer. It will have only transverse answer. We would like to know where the image will be. The answer is pretty simple. Any light ray coming from the object, any light ray coming from the object hitting the pole, this becomes the angle of incidence. And because pole itself will act as the principal axis will act as a normal, the light ray will go at the same. So wherever is the image, I don't know where the image will be. If the image forms somewhere here, I don't know. You can again drop a perpendicular from here to the principal axis. And we know the relationship between the perpendicular separation and all. So I can call it O. Let's call it A, B. This is the object. A becomes here A dash, B becomes here B dash. And this is the image. So from triangle, I mean similar triangle, you can choose or whatever. You can just write one line answer. You can write tan theta equals to, and theta is going to be same. So tan theta you can write as AB upon what you can write PB. Yeah. That's nice. And this we call HI, the height of image. Similarly, we can write the tan theta as A dash B dash upon PB dash. Yeah, that's simple. So again, you can choose sign convention as you wish. You can call this as x-axis, and you can call this as y-axis. So you can take bottom as y. I mean, it really doesn't matter. So as per one of the convention, I am going to write the answer. So what we are deriving is called the transverse, and transverse we write by M symbol, but we write the longitudinal by the symbol ML to distinguish the unique scenario. So what is M here, by the way? M will be what? Size. Size means A dash B dash upon AB. That's it. That's it. That's called the size. I mean, basically, what you write is not size. You can write as height of image upon height of object. Okay, this is called magnification by definition, and it's always a positive value because magnification is a number, but it can come with sign plus or minus to interpret the nature of image, and the nature will be real or virtual. So what we come to know that any real image of real object, if the real object forms a real image, the magnification must be negative. because it will invert. And if real form virtual, it means the magnification must be positive because it will never invert, it will keep it erect. So if the object and image are having similar orientation, both up or both down, the magnification will be positive. If they have the inverted orientation, like one up, other down, or vice versa, the magnification will be negative. But let's see how to derive this easily. So we will substitute the value here, tan theta, with sine properly. What is AB? It's above the axis. We can write as plus H naught. PB minus A dash B dash minus HI. PB dash minus V. And this will give you what? HI by HO is basically minus V by U. Can you see that? We derive using the proper sign convention. We substituted the all symbol with proper sign. So we took up as positive, down as negative as per the Y is there. But the M is defined as HI by H naught because HI, H naught were values actually, which turns out to be minus V by U. So we write M equals to minus V by. So for mirror, it's very easy to derive. If you forget, you can just draw this similar triangle quickly and get the answer. Always learn the derivation, not the just formula. Try to understand what we are doing here and what we take care while deriving, like convention, sign convention, and so on. So magnification becomes minus V by U. M is HI by H naught. You can always equate these two relations. So this is something you can always use. Magnification is negative. It means one is real, other is virtual, and vice versa. Sorry, both are real. Real object, real image, or virtual object, virtual image, maybe something like that. Okay, so what else we can do now? Yeah, longitudinal. So how we define longitudinal? For that we need to keep the object along the principal axis. Maybe I can keep some. So let's say we have an object. I'll take a small example. Kept near C. If the object is near C, the image of this part will be, this portion will form the image exactly there only, because anything at C will form the image at C only, correct? But anything beyond C will form image on the other side. So anything left of C will form the image on the right side. So this end will be somewhere here, maybe here. And not only that, it will be a smaller size, something like this. So roughly, don't take it exactly. This object, which looks rectangular, will form an image like a trapezium. But when it comes to the longitudinal magnification, we only look for the size, like the dimension along the principal axis. We don't take. So it is quite possible that this end we can call U1, this end we can call U2. I mean, luckily U1 and V1 are same. And for the object, we can call this end as V1, this end as V2. It's the other way around actually. This is V1, this is V2. Okay. So the longitudinal magnification only depends on the distance of the end point of the object along the principal axis. And the way of writing is pretty much simple. So we write a V2 minus V1 upon U2 minus U1. Simple. Just need to check the distance, like how far. So the nearest distance from the pole, the farthest distance from the pole, take the difference, and also take the difference of the image in a similar order, and take the ratio that will be called longitudinal magnification. Now this is very important in certain situation when the two. Oh, so what if U and U2 are very close? So if I call U1, so now we have something called a special case. For tiny objects, it becomes really interesting. If I call U1 as U and U2 as U plus DU, like very close, and V1 as V and V2 as V plus DV, like slightly ahead. In such scenario, what I'm writing here, the AML becomes what? Which is the differentiation of V with respect to U. And why this formula is so useful? Because we know the mirror formula. F is a constant quantity because for paraxial F is going to be fixed value. If you differentiate, this will 1 by V square into dV and du by u square equals to 0. The dV by du turns out to be minus V by u whole square, which we can also think as that longitudinal becomes the square of the transverse or linear. That's very important relation. It means the object is not big enough to be called 2 points, rather you can take as 1 point, and assuming single point you can find the linear magnification formula, and if you square it you get the longitudinal. That's simple. ML is always minus of m square for tiny objects. Okay. So if how to understand that, I have to apply this formula. If the focal length is in centimeter, object is in millimeter, always choose the tiny assumption. Okay. So such assumption will help you in solving some more difficult problem. So I think I should stop here. Something is left from the mirror, but now you can start solving the question from the spherical mirror. So I think I have shared the sheet from the resonance. The optics sheet I have shared, isn't it? Tell me, yes or no?
Sir, I don't think you have sent, but I will check.
Just a moment. If I have not shared, I will share right.
Sir, you have shared a PDF of
Yeah, optics, no?
array optics PDF.
It's a handwritten notes or
Yeah, the
the
handwritten.
just a moment.
So you sent resonance questions that optics one.
I have sent, no? I think I've sent in the very beginning.
Yes.
Anyway, if I have not sent, I will again send.
Yeah, sir,
You
can
have
you
to-
send again?
Yes, just a minute. Mm, all right. So now you can start solving. Let me just tell you what you can solve. You can solve the exercise 1 part 1 plane mirror part completely. You can now solve all of the spherical mirror questions. So part B you can also solve from everywhere. So I expect that you guys will start solving now. Finish the plane mirror as soon as possible and start the spherical mirror. solve every question. I will take some tough question in the next lecture, but I hope you can do the rest. Yeah, everything is easy only. All right, guys. Bye and take care.